The sun is great. It is so far away from the Earth. The solar panel is so small, but the motor can still be powered and rotates fast. Solar energy is powerful.
Solar power is one of the most important sources of renewable energy. It converts solar energy into electrical energy. It helps reduce the use of fossil fuels for generating electricity and reduce the emission of greenhouse gases to alleviate climate change. The efficiency of a solar panel is affected by many factors. Let's learn more about it.
Thank you. Let me take more data. It's changing. What about here? It's lower. It seems better here. Oh no, that's so strange.
Tissue, can I ask what you're doing with the solar panel?
Dr. Tong, I wonder how to make the solar panel work at optimal efficiency. The number keeps on changing. I lose track of it.
Experiments cannot be done in this way. When light is incident on the solar panel, the angle of incidence or other factors will affect its output power. To carry out experiments, we have to better control the apparatus to get meaningful results. It is better done in a laboratory.
How do we do it in the laboratory? There's no sunlight.
Follow me then.
Okay. Dr. Tong, it's obvious that the closer the light source, the brighter my hand is.
Of course, we know it from daily experience. When a lamp is further from us, it looks dimmer. When getting closer, it looks brighter. The relationship between illuminance and distance can be verified by an experiment. Can you lend me your smartphone?
You have your own smartphone. Why do you want to take mine?
Smartphones are very useful. The LED of your smartphone can be used as a light source. My smartphone has a light sensor. It can be used as a light meter. With a suitable app, the illuminance on it can be measured. We can fix the smartphones with these two stands. Here are 2 meter rules. We can move this smartphone to change the distance between the 2 smartphones. From the reading, we can find the illuminance. We can then study how the illuminance changes with distance.
Okay then, here you go.
The 2 smartphones are here. The LED here serves as a light source. The light meter here measures the illuminance. The unit is lux. To reduce the influence of ambient light, we will turn off the light. We will change the distance between the light source and the light meter by moving it along the track. At each distance, the reading of illuminance is taken. There is one more thing to note. We aim to measure the illuminance due to direct light, but not the reflected light caused by, for example, the reflection by the bench. The reflected light should be subtracted. The way of achieving this is to use this black cardboard to cover the light meter. The direct light is blocked. This background reading is due to the reflected light. By recording the reading and then subtracting the background reading, we can obtain the illuminance due to direct light. Let's begin with 20 centimeters.
Sure.
Let's see the data. Let's increase the distance to 30 centimeters. Okay, increase the distance to 40 centimeters. 60 centimeters. 80 centimeters. Lastly, 100 centimeters.
We have got the data, How do we analyze them?
We are verifying the inverse square law. That is, illuminance is inversely proportional to the square of the distance. To put it simply, let's say we start with a distance and obtain an illuminance. When the distance is doubled, since the illuminance decreases with the square of distance, it will become 1 over 2 squared equals 1/4 of its original value. If the distance is tripled, the illuminance becomes 1 over 3 squared equals 1/9 of its original value. If the distance is 4 times as large, the illuminance becomes 1 over 4 squared equals 1 over 16 of its original value. How can we verify such a relationship? We can plot the illuminance against 1 over r squared, where r is the distance. If the inverse square law holds, the graph should be a straight line.
Why is there such a relationship between illuminance and distance?
You can imagine there is a tiny light source. The light it emits is evenly distributed in all directions. When the distance from the light source is r, the energy of light is distributed over a sphere of radius r. The surface area of the sphere is 4 pi r squared. Given that light is distributed on the spherical surface, illuminance decreases as the spherical surface gets bigger. Thus, illuminance is proportional to the inverse of the area of the sphere, i.e., proportional to 1 over r squared.
Does the distance between the Sun and the Earth affect solar illuminance and hence the efficiency of solar panels?
The Earth revolves around the Sun in an elliptical orbit. The Earth is sometimes closer to the Sun and sometimes farther from it. But the orbit of the Earth is still very close to circular. The change in distance is small. The distance between the Earth and the Sun is almost constant, so it has little effect on the illuminance. When solar panels are installed on the Earth's surface or on the satellites orbiting about the Earth, the illuminance is not affected by the change in the distance of the Sun. However, if we are not near the Earth but exploring other planets such as Mercury, which is closer to the Sun, or Jupiter, which is further from the Sun, the change in distance from the Sun becomes significant. In these cases, the efficiency of solar panels is affected significantly.
I see. Sunlight is very intense. Do solar panels produce a lot of electricity?
That is true. But the efficiency of solar panels is not directly proportional to the illuminance. It does not increase indefinitely with the illuminance. This experiment aims to find out the relationship between illuminance and the output power of a solar panel.
Are we using this?
Yes.
This is a spotlight for filming. I got it. It's used to simulate the sun. Why don't we just put the solar panel under the sun?
We cannot change the intensity of sunlight, and so we cannot change the illuminance. But the brightness of this spotlight is adjustable. We can change the illuminance on the solar panel. The solar panel will be placed here, under the spotlight. A smartphone will be placed beside and serve as a light meter. In this way, we can measure the illuminance near the solar panel. How do we measure the output power of the solar panel? We measure the power provided to this resistor. First, the resistor is connected to the solar panel. Here are 2 multimeters. One of them measures the current passing through the resistor. The unit is milliamperes. The other measures the voltage across the resistor. The unit is volts. Power is the product of current and voltage. The unit of output power is milliwatts. Let's start the experiment. You may adjust the brightness. The illuminance is about 14,600 lux. You may record the data. Output power is the product of current and voltage. Let's increase the brightness. 30,000 lux. Further increase the brightness, 42,600 lux. Increase the brightness, 59,500 lux. Increase the brightness, 82,600 lux. Increase the brightness, 113,000 lux. Increase the brightness, 136,000 lux. Increase the brightness again, 160,000 lux.
We've got many data. What is the conclusion?
Let's sort out the data first. Then, we plot the output power against the illuminance. The y-axis is the output power and the x-axis is the illuminance. From the graph, we see that at low illuminances, like tens of thousands of lux, the output power increases with illuminance. It is close to a linear relationship. The output power is almost directly proportional to the illuminance. However, at very high illuminances, like over 100,000 lux, the output power does not increase rapidly. The curve flattens. At 100,000 lux or so, the curve reaches a maximum. This shows that the output power of a solar panel has a certain limit. It cannot be too high. Even if it is over 100,000 lux, the output power does not increase further. This is closely related to the practical application of solar panels. In outdoor areas, the sunlight can be very intense, with over 100,000 lux. In this situation, the output power of solar panels may have reached a saturation level. It cannot increase further. We can also see that the weather has a significant impact on the output power of solar panels. On cloudy days, sunlight is weaker. The output power of solar panels is smaller.
The output power of solar panels cannot increase indefinitely.
We should know the apparatus limits to make better use of it and improve the efficiency. Tissue, what are you doing with the solar panel?
Dr. Tong, I just randomly oriented the solar panel under sunlight. The reading was changing from time to time. I was thinking about whether the incident angle of sunlight affects the output power of the solar panel.
That is a good observation. The incident angle of sunlight indeed affects the output power of a solar panel. You can imagine that when sunlight is incident normally, the solar panel receives the most sunlight. That power generation should be the highest. How about if sunlight is incident obliquely? For the same light beam, when it is incident obliquely, it is distributed over a larger area. The sunlight spreads over a larger area, so the illuminance decreases. The output power of solar panels also decreases.
What is the relationship between illuminance and the angle of incidence?
In physics, we have Lambert's cosine law. It states that the illuminance on a surface is directly proportional to cosine theta, where theta is the angle of incidence. Let's see how cosine theta changes with theta. When theta is 0 degrees, meaning that the angle of incidence is 0 degrees, cosine theta equals 1. The illuminance of the surface is maximum. As theta increases, the value of cosine theta decreases. So, the larger the angle of incidence, the lower the illuminance. I have an experimental setup to illustrate it. Here are two smartphones. One serves as a light source. The LED of this smartphone is the light source. The other smartphone is a receiver. We make use of the light sensor in it. With a suitable app, it can measure illuminance. We will rotate the light source fixed on the farther end of the arm about this smartphone. This changes the angle of incidence. At each angle of incidence, we will measure the illuminance on the smartphone.
Let's begin.
Sure. The angle of incidence is 0 degrees.
The illuminance is 510 lux.
The angle of incidence is 10 degrees now.
The illuminance is 505 lux.
The angle of incidence is 20 degrees now.
The illuminance is 484 lux.
The angle of incidence is 30 degrees now.
The illuminance is 450 lux.
The angle of incidence is 40 degrees now.
The illuminance is 398 lux.
The angle of incidence is 50 degrees now.
The illuminance is 301 lux.
The angle of incidence is 60 degrees now.
The illuminance is 111 lux. Dr. Tong, what do the results show?
With the data obtained, we plot the illuminance against the angle of incidence. When the angle of incidence increases, the illuminance decreases. Then, we plot another curve of the theoretical values of illuminance against the angle of incidence. When the angle of incidence is 0 degrees, the theoretical value is the same as the empirical value. When the angle of incidence is larger than 0 degrees, we assume the illuminance changes with cosine theta. The theoretical and empirical values agree well when the angle of incidence is small. At large angles of incidence, the curves deviate from each other. Why does it happen? When light is cast at large angles of incidence, some of the light is reflected by the glass surface of the smartphone and cannot reach the light sensor. That is why the empirical value of illuminance decreases faster than the theoretical value.
After all the discussions, what are the factors affecting the angle of incidence of sunlight?
In real situations, there are many factors affecting the angle of incidence of sunlight. The sun rises and sets daily. Sometimes it is high in the sky. Sometimes it is near the horizon. The angle of incidence is also affected by seasonal change. I will talk about this later. All these factors affect the efficiency of solar panels.
Oh no, we had a long conversation. It's time to adjust the inclination of the solar panels. I'll be right back. As far as I know, sunlight is not that simple. Apart from visible light, it contains some invisible things, such as ultraviolet radiation that can tan our skin. What is their effect on solar panels?
You are right. Apart from visible light, sunlight contains infrared and ultraviolet radiations. The upcoming experiment aims to test the response of solar panels under these radiations and see if electricity can be generated. We will compare different types of solar panels. This is a monocrystalline solar panel. This is a polycrystalline solar panel. This is an amorphous silicon solar panel. They are placed in this position. Here are two stands. What are they for? They are for placing the lamps. The lamp is fixed here. The distance between the lamp and the solar panel is fixed. For a fair test, the intensity of the light source is also fixed. Then, the solar panels will be placed one by one. How do we measure the output power? We use a resistor to do so. Here is the resistor. The electrical energy is provided to this resistor so that we can measure the output power. Do you remember how to calculate electric power? It is the product of current and voltage, i.e. P equals IV. How do we measure the current and the voltage? We have two multimeters. One of them measures the current passing through the resistor. The unit is milliamperes. The other one measures the voltage across the resistor. The unit is volts. Multiplying the two numbers gives the output power. The unit is milliwatts.
Let's begin with the experiment. Which one do we start with?
Let's start with the infrared lamp. We put it here. Then, we place the solar panels under it. Let's use the monocrystalline solar panel first. The solar panel is connected to the resistor, so that it starts providing energy to the resistor. You may record the values of current and voltage. Multiplying the two numbers gives the output power. Let's use the polycrystalline solar panel. You may record the values of current and voltage. Multiplying them gives the output power. Let's use the amorphous silicon solar panel. You may record the readings and calculate the output power. We have finished the test with the infrared lamp. Now it is visible light's turn. Here is a spotlight for filming. We put it here and adjust it to a certain brightness, which is kept constant. Let's start with the monocrystalline solar panel. You may record the current and voltage and calculate the power. Let's use the polycrystalline solar panel. You may record the data and calculate the output power. Finally, we use the amorphous silicon solar panel. You may record the data and calculate the output power. We have finished the test with visible light. Let's move on to the ultraviolet lamp. Ultraviolet radiation is harmful to our eyes. Before the experiment, we should put on safety goggles first. Let's switch on the UV lamp and put it here. We begin with the monocrystalline solar panel. Record the data and calculate the power. Then we use the polycrystalline solar panel. Record the data and calculate the power. Lastly, we use the amorphous silicon solar panel. Record the data and calculate the power. We are done.
The data are here. Under each of the radiations, the output power of the monocrystalline solar panel is the highest, while that of the amorphous silicon solar panel is the lowest.
Yes, the efficiency of monocrystalline solar panels is the highest. The performance of polycrystalline solar panels is a bit lower. The lowest is the amorphous silicon solar panels. Although the efficiencies of the solar panels are different, in general, you see that the solar panels are more responsive to visible light and infrared radiation, and less responsive to ultraviolet radiation. But there is one important thing to notice. The radiation powers of the three light sources are different. Therefore, we cannot compare the output power of a solar panel under the three different radiations. Still, we can roughly see that the effect of visible light and infrared radiation is higher. What can we compare then? Since the power and the distance are fixed for each light source, we can compare the performance of the three types of solar panels under each radiation. As I said, the monocrystalline solar panel is the best.
After watching the experiments, we know that monocrystalline solar panels are the most efficient under different wavebands of EM waves. I'm on the rooftop of the EMSD headquarters. The arrays of monocrystalline solar panels are installed here. The system consists of over 2,300 electricity generating modules. Each module consists of 72 monocrystalline solar cells connected in series. They appear as the rectangular panels you see here. The direct current output is converted into alternating current by a number of inverters. The electricity is supplied to the headquarters. The maximum output power of this system is 350 kilowatts, which is equivalent to 3 to 4% of the total power consumption of the building. Solar energy is an important source of renewable energy. In recent years, EMSD introduced the Solar Harvest Scheme to subsidize schools and welfare NGOs to install solar energy generation systems and help them join the Feed-in Tariff scheme. The beneficiaries can save on electricity bills while using more renewable energy to support decarbonisation work.